Hello and welcome to the continuation of a very interesting video. In the last video we talked about the differential amplifier and I showed you a simple configuration and how you can build a differential amplifier. And in the last video we also discovered that this configuration has some problems. It has some common mode problems and it also has some balance problems. So the output signals on both sides should be actually should have the same amplitude, but phase shifted, but they don't have the same amplitude. They are as this, so one side is bigger than the other side. And what we also saw is that if we connect the same signal to both inputs, the output should be 0, but actually it isn't 0. It was I think 4 volts or so. So the gain, the common mode gain was 2. So basically this was not a good thing. And now let's see how we can improve it. Maybe it's not too hard because I already told you everything which you need to know how to improve it. And the actual way to improve it is pretty simple. The only thing you have to do is to remove this resistor down here and replace it with something else. And what is this something else? If we went through all of this in the last video, so if you haven't watched it, please watch it. But the conclusion of this thing was that the problem was caused by one simple thing, and this one simple thing was that the AC cathode current, the AC current flowing through this resistor was not 0. It should be 0. The DC current for the operating point should be 1 or 2 milliamps or so, whatever we said. I think it's 2 milliamps in this circuit. And the cathode current AC wise should be 0, but it isn't 0 because here we have a voltage down here which changes a little bit, and if we have a changing voltage on a resistor, then we get a current change. So the small voltage change causes a small current change, and this small current change then causes that the circuit is out of balance and that it has some common mode problems. Again, if you haven't watched the first video, please watch it because it's very important for understanding what I will tell you now. And now to solve it, it is quite clear. We just have to put a current source down here. So we have to put a current source down here so that we get an actual constant current. So if this is an ideal current source, then the current flowing down here, so this should also then be the current source, so that the current flowing down here is actually constant, it is fixed, and then this here actually is true, and then we get no more common mode problems or no more out of balance problems. So just go through to this again. So if the cathode current, which is the sum of both currents flowing down here, if this is actually constant, and for AC if it is actually 0, then this means that the plate 1 and plate 2 currents are actually equal, except that one is minus and the other not. So we have an inversion going on here, but the amplitude of both signals then is equal, and this is what we like to have. So actually in reality it won't be absolutely 0 because every current source, no current source is perfect. By the way, there are different symbols for current source. You could also draw it like this. So now my pen gets empty, my marker gets empty. So you could also draw it like this, or you could draw it like something like this with an arrow down here, just to show there are a couple of different ways how you could draw a current source, but now I've chosen to draw it that way. And the next question is, how can we actually implement that current source, this current source? So what can we do? So we need a specific component which acts as a current source, and it is hiding under here, as I told you before. So now let's reveal it. Let's see what actually the solution for this is. So let me put it here. So the solution for this is just a simple pentode connected in a way so that it acts as a current source. So actually this point here must be connected here. So just connect this point here to ground. So this here, this current source is actually this here, just plug it into here, so we have the cathode current flowing through here. And how does this work? How does how can it be that this is a constant current source, you might ask? And to answer this question, we will have a short look into the data sheet of this tube. This tube is actually a pentode, and this specific tube is a 6AU6, but it will work with many other pentodes as well. And yeah, we have to look up characteristics of this tube in the data sheet. So here we are looking at the output characteristics of our 6AU6 tube. And what does this mean? Here on this axis we have the plate voltage, and on this axis right here we have the plate current. And these curves here are at a specific grid voltage. And if you don't know how to bias such tubes, I have already made a video in which I show you how to compute a simple audio amplifier, how to set the bias points of a simple audio amplifier with triodes and pentodes, actually with one triode and one pentode. And you can check out this video how to do that. But actually, if we set a constant grid voltage, let's say -3 volts on the grid, then we are on this line here. And the cool thing here is, if we set it to a specific voltage, then we get a specific current, of course. And you can see this line here is very, very flat. And this means that even if the plate voltage, which is the voltage on the anode of our pentode, even if this voltage varies, if it goes up or down, it does not matter. The current is the same. The current is still the same. So this pentode then acts as a constant current source because of its output characteristics. So you can use this pentode as a perfect constant current source. It is as simple as that. You just have to set this voltage. There's of course also a voltage for the second grid which you have to set, but just set this voltage, the voltage of the second grid, and you get a constant current output, which is extremely useful and extremely cool. Notice that I stabilized the voltage on the screen grid with this capacitor, and this improves its current source stability when the input is changing very fast for alternating input loads. And so that's why this capacitor is here, and then the current which flows down here is a constant current. So this is the solution to our problem, and now I will show you this solution in action. Of course, as you have seen in the first video, I've already prepared everything. Here we have the pentode, which we will use. The 6AU6. It's also printed on here. Maybe you can read it, but you don't have to. Actually, now I will plug it in. And now I have to change the circuit a bit so that the current source is actually in the circuit. So I will remove this common cathode resistor. I will just put it aside, and I will connect the current source here. Actually, one note is that this thing is now actually not acting as a current source. It's actually acting as a current sink because it draws current in it. A source would give current out, but this thing is actually a current sink because it draws current. The load is above the current sink, so therefore it's a current sink. And if it is a current source, then the load would actually be below the current source. So this is actually a current sink, but yeah, just that you have heard it. And yeah, now let's move to the oscilloscope and repeat the measurements which we did before, but now with this current sink. So first of all, we will test it in the differential mode. So I will connect the second input to ground, and the first input to the signal as we had it in our first test, in our first video. So now it's hooked up that way. So first input is to signal and second input is connected to ground. And now let's turn on the circuit. Now you can see the tubes heating up. And there we go. So let's first of all measure the gain. The input is still the same as in the last video. It's 2 volts peak to peak. And the output on the second channel is 55.4 volts peak to peak. So this gives us a gain of 27.7, which is exactly the same which we had in the first video. But now more interesting is how this change with the current source has improved our circuit. So just to make things a bit clearer, I removed the input signal from the screen, and if we can look, or if you can look at the measurement, you can see that the peak to peak voltage, I will freeze it, that the peak to peak voltage of the first output is 55.2 and the second output is 55.4. So we have 55.2, 55.4, and this is actually a huge improvement. In the last video I showed you the ratio of voltage 1 to voltage 2, and I will do the same thing again. So I will divide voltage 1 by voltage 2, which is 55.2 divided by 55.4, and this is actually 0.996. So it is much closer. Actually, I think it's even better than that, but I think that this could even be a measurement error. So I think it's so close that we cannot even measure it now. We cannot even measure the difference. If I turn on the cursors, so you can see they match up perfectly. Can you see that? They match up perfectly. So I think they are absolutely equal, okay? And as you can see, this is also a bit varying, 55.4.2, and yeah, so of course, so they are now, it's now in the noise, so the measurement, we cannot measure it that way, so it's that low, it's that good, and this is a huge improvement. So we fixed the out of balance issue, so it's now perfectly in balance, basically because the ratio is so much better. So actually the ratio is not even measurable with our setup, so it's a huge improvement. Okay, so this is for the out of balance thing. And now let us measure the common mode gain. So first of all, of course, I turn it off again, and then I connect it in the common mode, and now I turn it on again. So now both signals have the same input. So here you can see the output if the common mode is if the input is common mode. And let me zoom in a bit because it's very low. If you remember the last video, it was so high that it was visible at this volts per division, but now it's much lower than that. So we have to increase to see it, and basically down here it's of course a bit unstable because it's so low, so it's picking up some noise. Okay, and now it's very hard to measure exactly with this automatic measurement. So what I will do now is turn off the automatic measurement, or stop the thing, and then I will measure it manually with the cursors. So, and the delta is about 110 millivolts or so. So our common mode voltage is now, the common mode output voltage is now 0.112 volts, and now we can compute the common mode gain, and the common mode gain is actually, for this we have again to divide the output voltage by the input voltage, in this case by 2, and we get 0.056. And if we compute the common mode rejection ratio as we did it before in our video, we have to divide the differential gain by the common mode gain, and this gives us a common mode rejection ratio from 494.494, so almost 500. So before, without the current source, we had a common mode rejection ratio of 13.44, and now we have almost 500. So this is a huge improvement to what we had before, just by introducing the current source in our circuit. So you can see it is really a huge improvement. So to sum up, basically the out of balance has vanished, and it is so small now that we cannot even measure it. And our common mode rejection ratio has improved by about 35 or so. So this is a huge improvement of what we had before without this extra current source. So it's extremely huge improvement. So of course I'm amazed what this current source did to the circuit. But this concludes our video about our differential amplifier and about the how we can improve our differential amplifier. So this is the second and last part of these two differential amplifier parts, and I hope you have enjoyed watching the video and maybe learned a thing or two. And yeah, as always, thanks for watching and bye.